Okay, welcome back, everyone. I hope everybody's doing good. And if you're not able to hear me or if there are some logistical issues, just let me know. Let me just bring up the chat. Okay, so again, welcome to this session. So today we're going to continue with where we left off last time, which is about reinforcement learning. So let me give you let me, before we jump into where we stopped last time, let me just go through some logistical details. First is assignment 4 is due next week, in fact, on April 20th. I know some groups have already finished questions 1 and 2, which were related to the material that was covered last time and the week before. So today's session is going to be useful and, in fact, necessary for many of you to address question number 3. Okay, so which is about something called deep Q learning algorithm and the underlying, I guess, deep Q network. Okay, so we'll talk about that today. So and with that, hopefully you can finish this question number 3 by next week and finish your assignment. Now, project is also due a week after that, which is on April 27th, with which is the day before the session on 28th, where you will also have an opportunity to discuss your projects. Okay, and since it's the last 2 weeks, I would say try to focus on more on why the problem that you picked, for example, suits deep learning approaches and so on, and perhaps your unique take on coming up with a solution. Okay, it may not be unique, but try to start from the problem and focus on uniqueness rather than improving numbers. Okay, improving numbers up to a certain point is fine, but we are not really concerned about the most performant neural network architecture for a specific applied problem. Okay, um, so that's just a quick tip. If you, since you many of you are already in progress and we've already discussed some of these in the intermediate check-in, so I hope you can finish up and do well on the projects. Okay. Any questions about the assignment and the project before I get back into the context of what we want to do today? Okay, so let me come back to the context. And of course, if you have questions, type it on the chat or ask me during office hours and so on. And you can also contact Attending and me during the next 2 weeks with respect to feedback on your project if needed. Okay. So let me come back to the context. So as I was mentioning earlier, we have been almost midway through this I guess very different set of material or topics compared to the deep learning architectures that we were seeing earlier. Okay, so and we started with A/B testing, sample inefficiency in A/B testing to and looked at multi-arm bandits. That was 2 weeks ago. And then we also looked briefly at contextual bandits. And then last week we spent a bit of time on introducing some basics on reinforcement learning, and we'll actually come back to a way to describe the reinforcement learning problem in a slightly better way using the notion of Markov decision processes. And that will give us a much more crisper notion of what a value function is. And that actually is the underlying, I guess, idea behind a solution strategy for reinforcement learning, which is Q learning and therefore deep Q learning, which is a part of your assignment. Okay. And last time I did not spend any time motivating reinforcement learning at all. So what I want to do this time is, let's see. I want to quickly show some videos of some advancements in, I mean, some, I guess, applications of reinforcement learning. So let me share my screen. Share. Okay, I hope everybody can see my screen. If not, let me know. I can't see the chat right now, but I wanted to show you a couple of videos, and I actually showed this in the um, first session. Um, so this is actually a video of a car, a prototype by this company called NVIDIA, and you can see, I mean, they were demonstrating a self-driving car, okay, and it was doing, it was navigating a circuit in a controlled environment. But this is a demonstration of a car, and the controls of the car, the steering and so on, is related to decision making, right? And so the algorithm which steers, there's an algorithm behind, taking actions in this car. The algorithm could be trained using reinforcement learning ideas. Okay. Similarly, let's go to, and this is a video from, I guess, last year. I don't have a more up-to-date video. This is a video by by Tesla, a car manufacturer, and you can see how the person is not touching the steering wheel, and they're trying to demonstrate um, that it can go from point A to point B and go on highways, merge onto the highway, and exit the highway, and so on. Okay. Um, I don't want to spend too much time on this video, but you can see that it's navigating without the person in the driver's seat touching the wheel. And so this control action of slight, steering left, right, not just binary, but various degrees of steering, stopping, lane change, and so on. These micro actions, so meta actions, sorry, not these very fine-tuned actions, this finer level actions, and also coarser level actions. These are all can be trained offline using a simulator for a car. And once you have simulator for a car, how do you train it? You can use reinforcement learning. You can use many other things, but you can also use reinforcement learning. And but coming down a couple of steps from there, one of the reasons and the variant of reinforcement learning that we'll be seeing today is mostly about interacting with simulators. And here's an example where the simulator is this Flappy Bird game like environment. And here the controller is to control this bird so that you can get scores. And the score is being reported at the top at the center of the screen, right? So so this is a step down from the realistic environments that we saw in the previous two videos, but this serves as a great starting point for understanding how RL solution strategies work. They interact with the environment, they send an action, which is, the bird should go up at some point, and then they get the screenshot, which is, hey, what happened in the next frame of this video, and they also get a sense of, hey, what was the instantaneous score, and so on. Okay. So the API is what we discussed last time, which is you send out an action and the environment responds back with what's the next state and what is the reward that you got because you took this action. Okay. And there's long-term consequences and all that. We'll get back to that in a second. Couple of more videos. I don't know if anybody's, I mean, many of you have played probably first-person shooter games. So this is actually a really old 2D game, Doom. And you can see again, a computer can learn to, go to different locations and destroy, opposing force and so on to maximize scores. Okay. So the reward signal is actually a scalar signal, which says, hey, instantaneously what you should do. And sometimes this reward signal is not available at every frame. For example, it can be only available probably at the end of the game, for example. That's called the sparse reward setting. Okay. And finally, DQN, which is the algorithm that is part of assignment for question 3, it rose to fame back, I guess, about 9 years ago, where the authors of that paper, which proposed the algorithm, proposed the algorithm and the neural network architecture underlying the solution strategy. They showed how it can actually the same thing, same solution strategy, in the sense the same neural network architecture and so on, can be used to work with multiple different environments. And these environments are all different games in the Atari game set. Okay, there were 50 odd games. And here you can see one particular game called Breakout. And you can see that agent is interacting with this game, which is the game is the environment here, and it has figured out how to balance balance the ball so as to maximize its score, and score is at the top. Okay. So and that's the algorithm that we will hopefully see in the assignment. We're not going to work with Atari environment. We are going to work with a control problem called cart fall, where you have to balance a pole on a cart by moving the cart left and right. Okay. So any questions about those videos that I showed? The Tesla car driving completely offline. So I want to understand what offline means. So yeah, I mean, um, offline in the sense that it is not connecting to the internet. Yes, of course, it's offline.
Yes.
Yeah.
My question is that connect to the internet or not?
It's not connected to the internet. Actually, that's a good question. I did not follow too much about what Tesla is doing, but in this case, the controller I think is in the software is in the car. Okay, otherwise there's going to be a lot of latencies when things have to go to a server and so on. Okay, so, but the manufacturer updates the software on the car yearly or whenever there's updates. Yeah.
Okay, then how's the car knowing which path is now traffic? How does the car avoid the traffic if it's not online? I mean,
No. So the maps information is certainly there. No,
okay.
I guess you were asking about control. The control algorithm is not, it's not pinging somewhere else to figure out what control action to take.
Uh-huh.
But there's metadata. The usual information that you as an human driver would get from the internet. That type of information. Yeah, of course you can get it from.
Okay, gotcha.
Um, okay. Let me come back to our where we are. Again, as I said, we have been looking at we saw online reinforcement learning, sorry, online learning and contextual balance before. We just started with RL basics. We just introduced policies and action functions. Sorry, policies and value functions, and I'm going to start from there today. And today we'll continue. Hopefully, we'll talk about Markov decision processes, which is a way to just say, what the exact optimization, what the objective function is. For example, in supervised learning, for example, if you're doing multi-class classification, hey, the objective function is cross entropy loss, right? And here's a function class, here's a neural network architecture. So we need to be as specific as that. So and that's where we are trying to introduce some concepts so that you can be very crystal clear in what you're trying to optimize and what is the objective function and so on. Okay, and the objective function involves describing what is called state action value function or a Q function, and that's the underlying thing for the algorithm called DQN. Okay, so hopefully we'll look at we'll start from this policies and value function definitions, look at Markov decision processes, as a way to describe these again, and then start pretty much get to the only one solution that we're going to look at for reinforcement learning here. There are many other solutions elsewhere, which is called Q learning, and it's basically just based on trying to get a better and better estimates of these value functions, okay, by interacting with the environment. That's the basic idea. And we look at some other, I guess, supporting ideas which kind of define this algorithm called Bellman equations, if there's time. But I want to finish off this session by talking about DQN, because that's what you'll try out and try out and play around with, given the example code in your assignment. Okay. So let me switch over to the slide deck. Okay, good. So where we were last time was we were talking about an RL agent. Think of an RL agent as a solution strategy, an algorithm which is able to look at states and suggest what actions to take at every state. Okay, so so the agent, while defining such an agent, like for example a function or a class that you'll define in Python, you would need to understand at least some components. Okay, so at the end of the day, the agent has to implement a policy. So a policy is nothing but it just says, hey, in the state, what action to take. Okay, if the agent knows this, then the agent can just look at a state and spit out, hey, this is the action that I want to take. Right? You can think of policy as just a function which maps some states to actions. But the agent can also maintain a couple of other objects, depends on what the solution strategy is. And these other two objects are, one is called a value function, which is a score that you can assign to every state. Okay, so if there are only 10 states, then it's easy to maintain 10 numbers. If there are a million states, then you run into a problem, or whatever, billion states. And so that's where I think deep learning, or some sort of, yeah, that's where DQN comes in the picture, and we're going to talk about that later. Okay, for now, just assume that value function is just a score that you can assign to every state. Remember, again, state is nothing but the same thing as a context, or roughly the same thing as a feature vector. Okay, so some measurement that you're taking about the environment. Okay, for example, the screenshot of the game, for example, at a given point of time. And finally, the third component is this model. A model is something that an agent can maintain. It's just a model of how the environment behaves. So in reality, if you're trying to create a self-driving car, there's a real environment, okay, where people move around, cars move around, and so on. But you can always have a simulator for such an environment, right? And we actually saw one of the names that we discussed. I briefly showed last time, something called Carla. It's a simulation testbed for realistic, I guess, environments where you can try out self-driving car algorithms. Okay, so so a model is nothing but a representation of the environment. It's useful if the agent doesn't have access to a simulator, and if you have a model of the environment, you can work with that and figure out a good policy. Okay, that's how it's useful. Okay, but it's also going to be useful for us to define um, our objective function in a clean way, and talk about value functions as well. Okay, so these three components are related, but an agent at the end of the day should have a policy. Okay, that's the essential ingredient. Um, where is the chat window? Okay. Sorry, I just wanted to bring the chat window up in case there are some questions. Yeah. So I think so. What we'll do today, at least the first few minutes, is actually link these three things together: policy, a value function, as well as a model, uh, using the formalism of Markov decision processes. Okay, it's just a name. Markov decision process is just a name for a way to frame the RL problem properly in terms of numbers, so that you can actually, in terms of some crisp objective function, so that objective function and so on, so that you can define what a solution is. Okay, so once you know what to optimize for, you can always come up with an algorithm to optimize for it, optimize it, right? For example, for supervised learning, as long as you say, hey, the objective is cross entropy loss, then you know how to optimize cross entropy loss, for example, using gradient descent. Okay, that's the solution strategy, but you need to define, hey, this is the objective, a squared loss or a cross entropy loss, and so on, right? So that's what we're going to do today for the first part. Um, so policy, as I said, is just a mapping from states to actions. So generally, I mean, we're representing it as a pi. So it's just a function going from states to actions. Okay, so if there are 10 states and 2 actions, then there's so many policies, right? So every state you can potentially take 1 or 2 actions. And so those are the number of policies, for example. Those are, if there's for every state, there's only 1 action that the policy suggests, then it's a deterministic policy. But sometimes policies can be also stochastic. They can say, hey, in the state, 30% with 30% probability, you should go right, and with 70% probability you should go left, then those are called stochastic policies. They just, I guess, are more general than the deterministic policies. Now, um, and last time I was just showing an example of if the environment is a board like this, a maze, where you need to, where, for example, the agent can take actions which are north, east, south, and west, 4 actions in every state. So the state is going to be each of these white cells. And so basically the agent's location. Okay, and you want to go from the start state to the end state. Okay, start is over here, and the goal is over here. And reward is basically you need to define a reward for every action that you take. That's the, remember, that's how the agent knows that it's doing good or bad. So at every state, if you take an action, the reward is always -1. Okay? It just means that you want to get to the goal fastest. Otherwise, otherwise you'll accumulate a lot of -1s, and so your reward is basically a huge negative number. Okay, and so you want to maximize your reward. Total reward is generally the objective here. Okay. Um, and and in this slide, I was just showing if the environment is set up, if the problem is set up this way, then an example policy is what's shown in the red here. Okay, so the red is just a graphical illustration for an example policy. I mean, that also seems like an optimal policy because it's literally the directions are such that you are actually getting to the goal. But if some of the red arrows are flipped or are turned around, that's also a policy. It's just that that policy may be a bad policy. Okay, and so the whole point of RL is to trying out different actions by trial and error, figure out what the best policy is. And this trying out happens generally with a simulator, or if you're already in a real environment, then you do that there. Okay, so there is actually a need for an agent to try out things to figure out what's the best policy eventually. Okay, that's how. So the way to solve problem and the way to collect data is really online. Okay, and that's where I guess it ties back to bandits and so on, where you need to make decisions based on what happened before. Okay, so um, so that's why this is also part of sequential decision making, I guess, paradigm. And so policy is clear. It's just a mapping from states to actions. So what's the value function? As I said, value function is just a score that you give to each state, and the higher the better. Okay, and what is it actually? It is a prediction of the future reward, prediction of the future reward, or cumulative rewards, you can say, that you can get starting from that state. Okay, so it's basically to say, if it's high, then this current state that you are in is good. For the current state that you are in, that the value is low, then probably it's a bad state to be in. Okay. And mathematically, this is the definition of value function, is just saying that, hey, if you're following a policy pi, okay, some policy, let's say the red policy, then the value of every state is nothing but the expected total reward that you can collect starting from that state. Okay, um, so here's an example. If you're in this state, let's say, if you see the bottom right side, I underlined a particular, I guess, cell. So that's a state. Each of the white cells is a state. In that state, we are saying that the value of the policy, and the policy, let's say, is the red policy that we saw 2 slides ago. It said in this cell, go east, and then again go east, or go right and go right. Okay, and so therefore the value of being in the state, the state here, this white cell, okay, underlined here, this white cell, is, what's the reward that you collect if you take an action, right? Okay, and that's why you get an instantaneous -1 at that state. And also, what's the value you get in the next state, okay, by executing the same policy. So that's again -1. Okay, so two -1s add up to -2, which is the value of this state. Okay, similarly, the previous this state here, which is, I guess, overlined there, if you take an immediate action, you get a value of -1. From the next state, you take this right action or the east action, you get another -1. And again, you take an east action, you get -1. Okay, so that's why the value of this overlined state, this state, is -3. Okay, and similarly, you can backtrack and get numbers for every state, and that's the value function. And we are graphically showing the value function for this small toy setting. Okay, in general, I'm just saying that value function is just a mapping from states. So if you think of V as a function, it's going from states to some, let's say, real numbers. Okay, some number between anything. Okay, minus infinity to infinity. Okay. Um, and any questions here? Okay. We'll revisit value function and policy and model again and again. I mean, at least the next time. So in a minute, and we're going to talk about Markov decision process as a way to describe everything in a, everything in a nice way, so that you can relate policies to value functions and value functions to models and so on. So let me talk about models. Models are just a description of what happens in every state when you take a certain action. Okay? So for example, if you are in state S and you take an action A, what's the probability you'll get land in the next state S prime? Okay, so that probability is a transition probability model, okay, or transition probability function. Okay. Similarly, in a given state, if you take an action, what is the random reward you can get? Okay, and the average of that is this second model. Okay, it's the reward model. Transition model and the reward model are the two parts of a model that pretty much captures what the environment does. Right? Remember, environment has the following API. Given an input action, if you are in a current state, if the environment is in a current state, it says, hey, the new state is going to be st plus 1, and the reward that you get because you took an action now is rt plus 1. Okay, so the two things that the environment has to manage, and those two things are captured by these two parts. Okay, predict the next state or predict the immediate reward. Okay, um, so that's the model, and this is something that the algorithm, so that's as a solution strategy, for example, now in an RL problem could be that every time you can, you can, if you're an agent, let's say you are really a car, you can keep throwing different types of actions: steer left, steer right, steer left a lot more, steer left a little bit less, and so on, and try all those actions and see what the immediate reward is, and also what new state you went to. Okay, with that you can actually internally, you as an algorithm can construct how the environment behaves. Okay. Hey, if I steer left, instead of seeing the lane, I'm outside the lane, for example. That's the feedback you can get, right? I mean that feedback you can get through, getting the next state, but you can also get an intermediate reward. Hey, maybe you went into the payment, and so you incurred a loss, for example, right? So an agent can maintain these two objects in if it wants to optimize for a policy. Okay, but in general, the environment anyway, even if you don't maintain a model inside you as in a solution strategy, the environment is always going to give you a next state and a reward always. Okay, every time you play an action, it's up to you whether you want to how you want to figure out a good policy. Okay, you can always get a good policy by first reverse engineering how the environment works through constructing these two objects and then figuring out the best policy. Okay, but anyway, so we'll revisit this again. I didn't want to spend too much time on that. Um, yeah, and I will also skip this because it's just talking about how what's the model. Um, any questions about this part? I just wanted to uh, mention two things, right? Three things. A pi, which is a mapping from states to actions, a value function, which is a mapping from states to rewards, and we'll see another value function, actually, another one soon. It's also called a state value function. It's called a state action value function. And I also said a model, which there's three subscripts. Okay. It basically, so this and RSA. So these are, I guess, model components. Okay. And what we'll do next few minutes, maybe next 15 minutes or so, is just relate these three objects through the lens of Markov decision process. And I'm gonna really tell what Markov is, what a decision process is, what a process, why, it's a technical term here. And so I'll describe that next. Okay. But the purpose is to relate these three and then really get to a solution strategy for the RL problem. Okay, a solution strategy. In our case, it's going to be Q learning and eventually deep Q learning. Okay, and that's where DQN comes in. Uh, just to recap again, what we are trying to find in RL is to find something like pi star. Okay, what is pi star? It's the best policy. Best in what sense? It's the policy which collects the highest total expected reward. Okay, so let's say, yeah, in an environment, for example, the breakout example that we saw from the Atari games, it's a policy which balances the paddle at the bottom such that it bounces the ball and gets the maximum score. Okay, so that's what we want, a policy in every state, every screenshot of the every frame of that Atari game. You know what to do with the paddle at the bottom. Um, So these three components that I just mentioned, we're going to tie them together. Okay. The way we'll do that is a little bit, out of order. First, we'll talk about. I'll tell you the order in which, but you'll see that first we'll encounter value function, and then we'll encounter policies. Okay, so this is, I guess, number one, this is number two, and model is anyway, I mean, this is, I guess, number zero. So this is how we'll order things. I mean, this model will come at every I guess phase of this thing, but we'll first start with we'll first encounter a value function, and then we'll encounter a policy. Okay? And that makes the understanding of this object, or this I guess point of view, or concept called Markov decision processes easier. Okay. So and once we have this notion of Markov decision process, we can also think of, hey, how do we optimize for the best policy? So Markov decision process by itself, is just a way to describe the problem in a nice way, describe the objective, describe the problem in a nice way, and then we can get to how do we optimize it. Okay. So for that, the pathway that we're going to take is really start with the simplest building block. So first we'll start with something called a Markov chain. We'll explain what a Markov chain is, and then we'll go to a slightly, one more level of complexity, which is called a Markov reward process. And then we'll finally get to the idea of Markov decision process. Okay, and so Markov chain is something that you might have seen if you have done Gibbs sampling before. I mean, any of the previous course, like 572 or 575. If not, it's a very simple idea. We'll first recap Markov chains, then go to Markov reward process, and then go to Markov decision process. These are ways, and this formalism helps us really understand how we are trying to attack, how we are trying to, find a solution to this RL problem. Um, so yeah, what's a Markov chain? And here you'll see the model itself, the some resemblance to the model that we saw, a couple of slides ago. A Markov chain or a Markov process, okay, is just a name given to a sequence of random variables. Okay, a sequence of random variables. So what are the sequence of random variables for us? It's going to be a sequence of states, okay, a sequence of observations. Okay, so a Markov chain or Markov process is nothing but a sequence of random variables which follow a certain property. Okay, which by definition is the Markovian property. Okay, so what is it? So the Markovian property is as follows. If you're in state S, okay, remember we have a sequence of random variables. In fact, let me write it: S1, S2, ST, ST plus 1, and so on. Okay, maybe maybe it stops at 100 or something, or maybe it goes on and on. Doesn't matter. So for a Markov state S, and then successor state S prime. So let's say ST took a value S. Okay, because these are random variables, they have to take some values. Okay, each state, let's say, takes a few values. Then state S, ST took a value little s. Okay, now ST plus 1 takes the value S prime. Okay, now we're just saying that, and so the Markovian property is just saying that the probability of seeing um, probability of seeing state S prime given state S is the same as the probability of seeing state S prime given state S is equal to S. Okay, and whatever the values that the previous guys were taking. Okay, so S1 is equal to something, maybe alpha, maybe beta, and so on. It doesn't matter. So whatever these random variables are taking. So that's the Markovian property, forgetfulness property. Basically, that how did you arrive at state S subscript t? The capital S subscript t doesn't matter. Okay, this state doesn't matter. From this state onwards, only this state matters in where you end up next. Okay, so all the previous states don't matter. Whatever values the previous random variables took. The only thing that matters is what is the current random variable's value, little s. Okay, given that the current value is little s, what's the next state you'll get to is little s prime. Okay, that's a Markovian property, and that's captured by a state transition probability, I guess, probability function. Okay, that's p subscript s prime. Okay, and you can actually for every pair of such, let's say, by the way, all these random variables are on the same, I guess, support. Okay, they all take the same values, for example. Same range of values. So you can define a transition probability matrix. Okay, so you can say, hey, which is as follows, which is, let's say each state takes little n values. Each state random variable st takes n values. St plus 1 takes n values. Okay, what are these n values? Okay, each state, as I said, is a representation of the environment. Okay, So maybe each of the environment, let's say if it's think of screenshots, there could only be n different screenshots, okay, or screens, for example. Okay, and so the transition probability matrix is basically saying, hey, if I'm staying in state one, so little s1, the one of these n values, okay, in the current time step t, which is little s, then what's the probability I'll remain in the same state value? Okay? And similarly, you can say if I'm in state value little one, then what's the probability I'm still going to be in this what's the probability I'm going to be in state little n in the next time step, and so on. Okay, so this is nothing but probability that st plus 1 is equal to, let's say, n, given st is equal to 1. Okay? So it's basically, so this row is saying you are in state which is taking value 1. These are all the probabilities that you can be in 1, you can be in 2, you can be in 3, you can be in n in the next time step. Okay, so those are all these probabilities. Okay, and that's why they sum up to 1. The row sum is 1 because if you're in state 1, you can either stay in the same state, or you can keep going to different. You can either have the same state value next time, or you can have these other n-1 different state values as well, right? So they sum to 1. And so you can do that for starting from any specific state value. So my current state value could be 1, and my current state value could be 2. My current state value could be n. Okay, so that's the transition probability matrix. Okay, and so this is an example. So this is it's similar to the model that we have, except it doesn't have an action, but we'll add an action in a moment. And that's what a Markov chain is. A Markov chain is just defined by a transition probability matrix. And in fact, the way I've written it here, it doesn't depend on the time index. Okay, so the transition probability matrix, the transition probability is not depending. So this p of st plus 1 is equal to n given st is the same as p of st plus 2 is equal to n given st plus 1 is equal to 1. Okay, so the time index doesn't matter, and so that's this matrix. Okay, this is just a way to describe Markov chain. If you have this matrix, then you can figure out, then you can actually do a few things. First thing, let me give let's investigate this by an example. So here's an example Markov chain. Okay, so what are we seeing here is a graph. The graph has these things in circles or squares. The circles or squares generally represent a state value. Okay, so the value could be Facebook, the value could be class 1, class 2, class 3, and pub and pass. Okay, now if those are state values, then you know that we can have all pairwise probabilities, right? And those probabilities are given on these edges. Okay, so for example, if you're in class let's say 3, you can only go to this pass state, or you can only go to pub. You can't go to any other state. Okay, so which means that there is no transition to other ones, or the probability is 0. Okay, so that's what's captured, and there are some incoming arrows to each state value and outcoming arrows to each state value. So at any given point of time, for example, S1 could be sleep, and then there is no outgoing arrow, so you're sleeping. So but in some other I guess situation, it could be S1 is equal to Facebook. S1 is Facebook, maybe S2, since you can see that from Facebook there's only one outgoing arrow. S2 could be there are two outgoing arrows. One is to Facebook itself, or the second one is to class 1. So S2 could be maybe class 1, or maybe in some other situation S2 could be Facebook. So I'm just telling you what's the sequence of random variable realizations that can happen. So here, and that's precisely given here. For example, you can have class 1, class 2, class 3, pass, and sleep. So which is this arrow. I mean, you go from class 1, class 2 with 50% probability, from class 2 to class 3 with 80% probability, from class 3 to where are we going? To pass with 60% probability, and then from pass to sleep, it's 100% probability. And that's what this simple Markov chain is showing us. Okay, so you can have you can keep running this chain as much as possible, but you can see that all chains stop at some point, because once you get to sleep, there's no other next state cannot happen. Okay. So and here's an example of that transition probability matrix that I was talking about. So if you're in class 1, you can only go to class 2, or you can go to Facebook. Okay, if you're in class 3, we saw earlier that you can only go to pass, or you can only go to this other state path. Okay, so this is the probability, and you can see that the row sum is 1. Okay, 0.6 plus 0.4 is equal to 1. So that's a Markov chain. So any questions about Markov chain? What we will, as I said, we'll do next is introduce one extra thing, which is a reward, and another extra thing, which is an action, and that will give us a way to describe, um, an RL setting. Okay, if there are no questions, I would encourage folks to go back, and if you have done Gibbs sampling as a way to sample from complicated distributions, then it's a good idea to go back and check why Gibbs sampling also follows a Markov chain. Okay. Okay, now let's add one extra ingredient, which is a reward. Okay, so you have this chain, which is a sequence of random variables. So you're going from one random variable to the other based on this P matrix, basically this transition probability matrix. But when you're going between these states values, why don't we also generate some rewards, some extra numbers? Okay, so that's the idea here. So in every state, let's just spit out a flip another random variable, which is a scalar random variable, which produces a number. Okay. And so that, let's say the expected value of that, let's call this the reward function, script R subscript S. Okay, so that's the reward that you can get, expected reward you can get if you are in state little s. Okay, if you're in state some other s prime, you may get some other expected reward. Okay, and so to describe this extra numbers that you're generating when you're passing, moving forward in the Markov chain, is um, essentially gives us what is called a Markov reward process. Okay, remember, a process is just a sequence of random variables. Markov process just means memoryless property, that everything else before doesn't matter. What's the current situation, what's the current state value, that's what matters. And reward process is precisely because we added an extra reward random variables, extra reward random variables into the picture. Okay, and so to describe this, you can use these symbols. Okay, what is the first symbol? Is a set of states. Okay, a set of state values. Okay, 1 to n, for example. And script P, as we know, is a transition probability. Okay, what's the probability I'll go from 1 to 1? What's the probability I'll go from 1 to n, and so on, right? And script R is just what we just added, which is the reward function. There's one more number which we can add. It's a number between 0 and 1. It's called the discount factor. Okay? What is the discount factor? As we move forward in a Markov chain, let's say we start from some state. We saw some examples here, right? So if we start from some state, okay, let's say class 1, we keep going on realizing some values for states. Maybe it takes 20 steps, and eventually we'll get somewhere. Okay. So as I said, in every state in Markov reward process, we are going to generate a number. Okay, so a number. So if we add all those numbers, sometimes numbers, they may explode, in the sense that they may go, they'll grow large. Okay, to somehow, sometimes you may not want them to grow too large, and so you can always add the numbers with the multiplication factor for numbers coming later. Okay, that multiplication factor is called a discount factor. Okay, let's actually look at an example. Uh, so we'll look at an example in the next slide, but before that, because we added this discount factor, we can actually talk about a new random variable, okay, which is just the sum, which is the sum of these reward random variables, okay, but with this discount factor. So this new random variable GT is, random variable RT plus 1 plus this discount factor, which is, let's just think of it as, like, let's say 0.5, doesn't matter, some fixed number. So RT plus 2 times 0.5 plus maybe 0.5 square times RT plus 3 plus 0.5 to the power 3 t plus 4, and so on. Okay, till whatever time you stop the Markov chain. Okay, so that's called a return random variable. And with just that return random variable, we can actually define a value function. Okay, so we just had a Markov chain. We just added the extra fact that, hey, if you're in every state, just spit out a random variable. Okay, we spit out a realization of a random variable, RT plus 1, RT plus 2, and so on. Okay, let's aggregate them together. So in every state, you can every time step you can say what's the sum of the rewards, or what is some of these random variables from this point onwards. Okay, discounted. And the expectation of that number, that's called a return random variable, and the expectation of that number is essentially called a value function. Okay, so a value function for a Markov reward process is just the expectation of the reward random variable starting from that state little less. Okay, and so value function is a function of this little less. So this is just a map, right? If you're starting from the state little less, maybe little less is equal to 1, little less is equal to n, doesn't matter. Starting from the state, what is the expectation of all these numbers I can get from this state? Okay, maybe the sum is actually an infinite sum if the Markov chain never stops. Okay, a Markov chain never stops if there is no terminating state. But if there is sum of numbers, and that's why we have introduced a discount factor, because if there's an infinite such sum, as long as this gamma is something like 0.5 or something less than 1, uh, then that even if you are adding infinite number of numbers, they sum up to something which is finite. Okay, so that's the definition of value function. Any questions here of what a Markov reward process is and what's a value function here? And this value function is, you will see that it's the same as what we discussed when we're talking about the components of an RL agent. That value function, this value function are almost the same. We'll have to add an extra thing called actions. We'll add that in the next couple of slides. Okay. Yeah. So in the example, I mean, it's the same Markov chain from earlier, except in every state, we're just saying, hey, in fact, we're not even generating random numbers. We're just saying, hey, in every state, just pick a fixed number. So the random variable is not really random. Fixed number, which is -1, -2, -2, +10, and so on. So with these numbers, you can say, hey, if the sequence of, if my state variables realize in this way, class 1, class 2, class 3, and then pass and then sleep, then I'll accumulate certain set of numbers, right? So since I'm in class 1, I'll get -2. So that's written here. And since went to class 2, there's another -2. But class 2, I'm also discounting by 1/2 because gamma I chose to be 1/2. And similarly, class 3 is again -2, but it's gamma square, so 1/4. And similarly, pass is I get 10 units of fixed reward. It's not random. And then 1/2 to the power 3 is 1/8. Okay, so that sum is some number. Okay, that number is saying how good, for example, the state is. Okay, so the value of being in class 1 is equal to, in general, so sorry, it's supposed to be an expectation, but one of the trajectories, one of the trajectories is -2.25. Okay, but from the same class, I could have realized some other sequence of state values. Okay, and therefore a different sequence of rewards. So in some other trajectory of this execution of the Markov chain, I got a number which is -3.125, and similarly, and so on. So if I have 4 different situations, then maybe there's 4 different numbers. So this average is what is equal to the value function of being in state class 1. Okay, I mean, of course, if you have lots of such averages, a lot of such forward, executions, then if you take an average, then that's pretty close to the value of being in that state. And again, remember that value of a state just gives you a sense of how good that state is. Okay, in terms of expected future reward that you can get, expected total future rewards you can get from that state. Okay? That's why it's called value. Yeah. Actually, before we get into adding the next, I guess, ingredient, which is actions, we want to show you I want to show you a quick equality, which is going to be useful when you're thinking about Q-learning, as well as the idea of Bellman equations that will come later. So what is that equality? Okay, so remember, value function is just equal to this, right? It's the expectation of return random variable given the starting state is little less. That's just definition. But we know that the return random variable is equal to this expanding, this ever increasing sum. It's RT plus 1 plus gamma times RT plus 2 and so on. That's just, again, definition. Now, what you can do is for this part, you can take gamma common, and you'll have RT plus 2 plus gamma times RT plus 3 and so on. Okay. Now, what you can say is that this sequence, this sum is actually equal to GT plus 1, right? Remember, GT plus 1 is going to be, hey, I'm at time t plus 1, what is the sum of discounted sum of all the rewards that you can get, right? So that's GT plus 1 here. And what you can do is this expectation is over all the future randomness, okay? All the future randomness that can happen in, what states can realize and what rewards you can get. What you can show is that you know, uh, I don't know if you've seen this property. If you take an expectation over a random variable, let's say x1 and x2 of let's say the x1 plus x1 times x2, something like this, then you know that this, I'm just giving an example here, okay, to just explain what's going on. This is actually equal to expectation of x1 of x1 plus x1 times expectation of x2. Okay. Um, So basically, you can bring the expectation. This, as I said, this expectation goes to all the future. You can say, hey, let's take all the randomness from next step st plus 1 onwards and apply it to the inside. Because these are the random variables related to the future, right? From t plus 1 onwards. Okay, so you can take an expectation at that point itself. So this is actually equal to expectation of g t plus 1, okay, given s t plus 1 is equal to some value, which is, let's just call it st plus 1 itself, some value. So this is this expectation, right? And that's why the shorthand for writing that is a v of st plus 1. Okay. So this is a recursion. So v of st, this is an equality which is just relating two different evaluations of the same value function. Okay, so the value of a state little less is related to the value of this random state value that can happen in time t plus 1. Okay, so it's saying that it's the average of all the values that you can have at time t plus 1, because at time t plus 1 you can have a value equal to 1. Let's say the states are 1 to n, then in the at time t plus 1 you can have state is equal to 1, st plus 1 is equal to 1, st plus 1 is equal to 2, and so on, all the way to st plus 1 is equal to n. You need to take the average, and the values there are related to the values at the current state little less. Okay, so somehow it's a relation between the value at state little less, this side, and values at potentially other state values, right? So because st plus 1 is written in a capital letter, which means that it's a random variable. Okay, it has not realized yet, and so when it realizes, it could take any of the n values. Okay, and if it takes any of the n values, there's going to be value corresponding to them, right? Any of these state values that you are taking, and so v of s is related to um, sum over all the future things that can happen, s prime. Okay, s prime is equal to 1 or 2 to n, whatever, of okay, I didn't want to write this here because we actually have this expression in the next slide. So let me write it in the next slide, actually. Yeah. So let me explain this step again. So it's copied here, the same last step from the previous slide. So it's just saying that the value of at a given state is related to the values at other states in the future time. Okay, and in the future time step st plus 1. Okay, so at st the value is little less. Okay, and at st+1 we don't know what the value of the state is going to be, but whatever the values it's going to be, those values in expectation are related to the value at the current time step. Okay, so this expression, if you really expand it out, is the following. If you remember, we have, let's say, expectation of x plus y. This is by definition is equal to expectation of x plus expectation of y. Okay, so this is true for any random variable, any function generally, any sum function. Okay, if you have x plus y or x plus y square or x plus y plus z, expectation over a sum of random variables is just the expectation of individual guys. Okay, so you can say, hey, expectation of this plus expectation of this. Okay, now expectation of this conditioned on st is equal to s, the same conditioning here. Okay, that is equal to rs. Okay, that's what we saw in the definition of Markov reward process. Okay, and the expectation of the second term here, keep the gamma the same as before. The expectation is nothing but, you can say, hey, I'm in state S. What's the probability I'll go to state S prime? That's this probability, this number, times the value at state S prime. Okay, that's this number. Okay? I need to average over all the S primes that can happen. Okay, from starting from state little s. Okay, that's the summation. So this is nothing but um, the expectation of this underlying quantity. Okay, so yeah, and so this is where the recursion is. So if this value at a given state is related to value at other states. Okay, I'm calling it recursion, but don't worry about that. I'm just saying this equality relates the value at a state to values at other states. Okay, and that's a cool property to use when you design algorithms for the RL problem. Okay? And in fact, Q-learning uses this, so that's why I'm trying to talk about this here. So any questions about this, or any details that you want me to clarify, or the connection to the larger picture, just let me know. Okay, so I mean, so far what we have introduced is Markov chains, Markov reward process. In Markov reward process, what happened is we already introduced the notion of a value function. Okay, there was no policies and so on, but we already introduced the notion of a value function. Now the next step is to add actions into the picture, and that's why what we'll describe next is going to be called a Markov decision process. The previous two things, Markov chain and Markov reward process, there was no decision to make. It was just a sequence of random variables just evolving according to the transition probability kernel, or the transition probability function, or the matrix, and emitting out rewards, and you can always compute value function just using that information, that much of information. In Markov decision process, you get to choose, you get to influence what's going to be the next state. Okay, that's through actions. And let's say action is represented by a script subscript. Sorry, so this script A is just a set of actions. Let's say north, south, east, west that we had earlier. And so what will change? Okay, there are a few parts that will change. Okay, if there's an action set, let's introduce that into our, how we represent this, Markov, the stochastic process, okay, or this random process. This random process, as again, is the process for the state random variables. There's return random variables that are involved from the previous Markov reward process definition. Now, with those two, what changes is the following, right? So the transition probability function is no more just conditioned on the previous state. It is also conditioned on the the previous state or the current state, but also on the current action that you took. Okay, so you are in some state little less. The probability that you'll go into some state little less prime next time also depends on what action you took. Okay, that's little a. And similarly, the reward that you get doesn't just depend on what the current state value is, little less, but also depends on what action you took. Okay, so that's little a. Okay, that's those x. So basically, some extra conditioning happens in your definition of the state transition probability matrix, or the state transition probability function, and the reward function. Okay, and everything else remains the same. And this pretty much is a description of a Markov decision process, and this actually captures everything that we wanted to say when we were talking about the reinforcement learning problem. In reinforcement learning problem, we had states and actions and rewards, and states, environment would transition from state st to state st plus one. That's exactly defined by just use the description. Environment also returns a reward random variable. Its expectation is given here. Um, and who takes actions? This is going to be based on, this is what the RL agent would take actions. Okay, so the agent would influence what states you go next, and therefore what rewards you reap. Okay, now as well as in the future. So here's a slightly different example. I mean, it looks similar, but it's slightly different. Here, the actions are now the ones in the red, ones on the edges, which are in the red. So for example, if you're in state, let's say A, B, C, D, E, okay? Let's say in these states are now, these names. From these states, let's say in state C, okay? If you take the action study, you will go to state D. Okay? But if you take the action Facebook, you'll go to state A. Okay? So here the actions are deterministic, so there's no randomness here, but um, um, yeah, for example, if you're in this state, this is a special state where there is no action needed, you will always go to some either state E with 40% chance, state D with 40% chance, or state C with 20% chance. Okay, but everywhere else it's a deterministic transition. So that's an example of a Markov decision process. Okay, so with Markov decision process, we can now introduce the notion of a policy. Remember before with Markov chain and Markov reward process, there was no notion of a action at all. So there's no need for a policy. Now, since we can interfere and influence what's the next state going to be and what's the reward going to be, we can talk about a policy. A policy is just an influencer of how the states evolve. Okay, next state what's going to be, and what's the next state going to be, and so on. What's the reward going to be, and so on. Okay, and and so we can talk about talk about these. How do you influence this through a function which says in every state what action you want to take. Okay, and in general we can keep it stochastic. Okay, which means that in a state. There's some probability with which you'll take action little a, with some probability you'll take action little b, and with some probability you'll take action little c. Let's say there are three actions, little a, little b, little c. Okay, so you can talk about a stochastic policy like this. And in fact, we're also looking at policies which again don't depend on time index. Okay, so we are actually doing quite a few shortcuts here. Let's say the policy doesn't depend on time index. Okay, it only depends on the current value of the state. And then that stochastic policy can be represented this way. Okay, and it fully defines the behavior of an agent. Okay, so the agent says, hey, I'm in state little s. Then I have a distribution over, let's say, the three actions that I have, or the four actions, north, south, east, west I have, and I can play according to that. Okay, sample a random number according to that this conditional probability distribution I have, and play the action, whatever sample realized action that was realized. Okay, so for a fixed policy, so now here's the we just came from Markov chain to Markov reward process to Markov decision process. And here we define a policy. Now for fixed policy, actually we go back. Okay, if you give me a fixed policy, then I'm no more interfering with anything, right? So the policy itself tells what's the next state is, sorry, next action is, and so on. So once I define the policy, there's nothing else for me to do. In that sense, once you fix a policy, the state sequence is a Markov chain. Okay? And the state and reward sequence is the Markov reward process. So if I fix a policy for fixed pi, I get a Markov reward process and a Markov chain. Okay? The state's transition is just a Markov chain, and the state, and if you account for rewards, that just becomes a Markov reward process. Okay, and so for the fixed policy, Markov process is just the same states set. Okay? The second thing is going to be the probability transition function. Okay, the probability transition function. Remember, it was p. It's going from, hey, if you're in state one, what's the probability of going back to state one, or probability of going back to state two, or probability of going back to state n, right? So it was an n cross n matrix if there are n values for the state, right? So it's the same thing, but here we're calling it p superscript pi because remember in a Markov decision process, we also have to specify what the policy is. But if you already tell me what the policy is, it's like saying this, right? So I have P of st plus 1, okay, is equal to s prime, given st is equal to s, and at is equal to pi of little s. So you can see in this whole expression that the only thing, because I already told you pi, the only thing that you can change is little s. So this is actually equal to p, I guess, pi um, going to s prime given s, right? Something like that. So and going from, let's say, little s is, let's say, 1, going to let's say state s prime is equal to also 1, some number, okay, 0.3, let's say. So that's how you come back. Once you fix a policy, then you come back to a Markov chain, basically. Any questions about this slide? Okay, so let's move forward. And this, so this p pi is exactly what I said earlier. So p pi is just going to be equal to this transition probability of going to state rest prime if you're in state little s, and if you take an action A, okay? But you need to average out if it's a stochastic policy of all the actions that you would have taken, okay? Average out over all the actions you would have taken. And that's going to be this p pi of going from little state s to little state s prime. Once you have this object, this is exactly a transition, p pi of going from s to s prime. Okay, s s prime um, is exactly this. Okay, so this is just you are basically averaging out the impact of the action. Okay, and also using, because you know the policy, you're also you're using the policy, and so you don't have an extra degree of picking an action. Okay, similarly, our pi of s is exactly given pi. I know I can't do anything else to induce any changes in state. So given pi, I'll just average out all the rewards I can get, expected rewards I can get for each of the little actions A. Okay? If this policy happen to be deterministic, then this is nothing but script p of s to s prime for A, which is pi of s. Okay, pi of s. And similarly, this is nothing but equal to, if it was a deterministic policy, then this is actually equal to script r s at pi of s. Okay, pi of s is exactly equal to some specific action little a, right? So that's what. So MDP is just a Markov reward process, okay, for a fixed policy. And since that is the case, we can talk about value function again. Remember, we had defined the value function for a Markov reward process. So for a Markov decision process, if I fix a policy, it becomes a Markov reward process. And so I can talk about, hey, given a pi, it's a Markov reward process. And so I have a value function. So I have a value for every state given the policy of what's the, because I've already told you the policy, what's the total reward, total cumulative expected reward I can get starting from the state, little s, uh, because I use policy little pi, okay, because I use a fixed policy pi. Okay? So this is called the state value function. Okay, and why are we explicitly adding that extra adjective state is because there's another value function that we can define, which is called the state action value function, or just the action value function. Okay, it's a function it's going from state and an action. Okay, it's a function which is saying, hey, if you're in state s and if you take an action, let's say A, from then onwards, if you follow policy pi, what is the total expected reward you can get? Okay, it's like a little bit more, it's at least giving you 1 degree of freedom, because you get to choose at least one action. Okay, you have to follow policy pi. That's, as you can see, you have to follow policy pi, and in that case, it's a Markov reward process. There's nothing else to do. Okay, nothing else to control. But in state action value function definition, or the action value function definition, we are saying, hey, the first action you can pick whatever you want. Don't follow, if you want. If you don't want, to follow the policy. But from next state onwards, you follow the policy. Okay, and then you of course will collect a bunch of rewards, in expectation, and then average them out with discounts. that's going to be the state action value of being in some state S and taking some action A. Okay? So it's just the expected future return, okay? expected return starting from state S and taking action A, okay, and following policy pi from that, from next time onwards. Okay, so that's the state action value function. Any questions here? Okay, so next, let me, so what we'll do next is just, so at this point, we have already defined state action value function, okay, for a Markov decision process. At this point, we can jump a few slides and talk about the explicit objective function, and then talk about the Q-learning algorithm itself. But what I want to do is spend a couple of minutes talking about an idea called Bellman equations, or Bellman equations. Don't worry about the expectation here. Bellman equations, which kind of revisit this equality that we saw earlier. Remember, in Markov reward process, I had spent a bit of time saying that, hey, V of S is actually related to V of S primes, okay, and that was, for example, R of S plus some over some some S primes of V of S primes, something like this. Okay, so there was an expression like this, okay, which is saying that value function is related to other value functions. That idea is captured by this notion called Bellman equations, and they help design the algorithm. They help intuit why the algorithm should be the way it is. Okay, instead of directly describing the algorithm itself, it's better to understand why the algorithm is that way. Okay, when I say the algorithm, I'm talking about we are getting towards Q learning. Okay, that's the only algorithm that we'll see to solve the RL problem in the session. So, I'm just recapping the recursion. Okay, for for state value function, we already know this. Okay, so if you ignore the pi, this is exactly the equation that we saw earlier. Okay, so value at state S is related to value at the next state. Okay, value at the next state. The next state happens to be a random variable, so it's just an expectation over that. Okay, this we have seen before. Similarly, the action value function, the state action value function, also has this similar recursion. So q pi of s comma a, okay, depends on q pi of s plus 1 comma a plus 1. Okay, very similar recursion. It's almost as, and the way you arrive at this is the same idea. So state action value, so if there's a number, let's say 10 at some state and action pair, okay, that number 10 is related to the value you would have at at the next state and some other action. Okay, many of them. Okay, because there's an expectation. So maybe if there's a number 11 here, the number 11 is related to number 10. Okay, whatever this value is. So there's a bunch of equations. Okay, bunch of equations like this that every value function and every state action value function should satisfy for a given policy. Okay, so for every policy, you have a bunch of such essentially linear equations. Okay, linear because expectation is a linear operator, and you can see it's q pi is linearly related to q pi at some other values. Okay, and similarly, v pi is related to some other v pi at some other states. Okay, so there's a bunch of linear equations. Um, and let's ignore this diagram here for a second. So similar to what we wrote when we're looking at Markov reward process, this recursion for q pi of s, if you really want to talk about the linear equality, is that q pi of s is related to q pi of s prime a prime. Okay, where s prime a prime are this generic, other states and other actions. Okay, so it's so this is a linear relation because this is, generally expected reward is going to be a number. Similarly, transition probabilities are going to be a bunch of numbers, basically the model. And pi is, a fixed policy, remember. So it's also tells you what's the probability of taking an action a prime and so on. So the only thing which we don't know, if we don't know, is going to be the values. Okay, so values at different states, generally you would not know a beforehand, but they are related to, of course, the model and the policy in the following way. Okay, so if you have a policy and if you have the model, you can come up with values. Okay, and if you have values, generally values are defined for a given policy, and so that's how they are all related to each other. Okay, so half an hour ago when I introduced policies, values, and model, Here you can see how they're all related to each other. Okay, so these two arrows are related to models. There's a policy here, and there's also a state action value function here, or the action value function here. So this relation is just this linear equation, okay, linear in this state action or action value function. Now, there's linear relation, and that was Bellman expectation equation, and that's what it is. There's nothing more there. Uh, and now let's come back to the objective for RL. Remember, RL is to maximize the RL's objective is to maximize the agent wants to take action such that it maximizes the expected total reward the agent can get over a period of time, maybe 100 seconds or something, whatever, 100 time periods, right? So that, remember, let's say the agent has to start from somewhere. So let's say the starting state is little s, right? Starting state. Then V pi of s is explicitly capturing, hey, if you follow a particular policy, starting from some state, P pi of s is exactly the same, right? It's expected total reward, discounted reward that you can get starting from that state little s. So in fact, the RL objective is exactly this. Okay, this is the expected total reward, and you want to maximize for every policy. You will get such a number, right? This is the value of starting from that state s. For every policy, you'll get that. So why not maximize over all policies? Okay, so this is exact problem that you would like to solve in RL. And if you know the model, then it's actually not RL. Um, it's a fully known problem, and there also it's the same objective. Okay, so this is the objective function, and similarly, you can also say the same thing with the state action value function. So um, the state action value function is basically to maximize. So the RL problem is to find a policy that maximizes state action value function at a given starting state, and if you chose some starting action. Okay, so that's how, yes, we are setting up the objective for our RL problem. Okay, we have defined the objective. We have defined the objective in the first couple of slides, but here we are revisiting and saying, hey, what does the policy mean, and what does the objective mean? Okay, and it turns out, and we'll not get into why that is the case. It turns out that this, we want to maximize this, and we want to, if we maximize it, the maximum value, let's say it's called Q star. Okay, now we can have a Q star for every state and action pair, right? So there's going to be a Q star of S taking a value 1 and a action, let's say north, and S taking value 2 and action being south, and so on, and S taking value 3, action being another pair. So for every pair of state actions, there has to be there's a Q star defined, right? Now these Q stars themselves have a relationship with other Q stars, okay? Very similar to Q pi. So if you fix a policy, remember, if you fix a policy, then Q pi at a state action pair is related to Q pi at some other state action pairs, okay, in that linear equation that we saw. Similarly, the this optimal Q value, state action value, but at a given state action pair, is also related to other state action pairs, and the relation is actually almost very similar, except the only change is this extra max operation, and this is essentially uh, the important, it's called Bellman optimality equation. I think I wrote it somewhere here. Yeah, Bellman optimality equation. Okay, this is the important equation, which is what I think folks in computer science, this is the dynamic programming recursion equation. So some of you may know it. If not, we will accept for as a fact that the optimal state action value function also follows a linear relationship, a linear, I guess, equation. Okay, it's a but okay, it's linear in the sense that there's an equality between state action value, optimal state action value at some state action pair s comma a, and the optimal state action value at some other pair s prime a prime, but it's not related linearly. Okay, so this is an equation, but it's not a linear equation. Okay, there's a extra max operation. Max is generally a non-linear operation. Okay. Um, that's called Bellman optimality equation. Now, this equation is saying, okay, so if you freeze some previous slide, what we were supposed to do is, hey, start with a pi. If you think, go back to how we were doing it for supervised learning and in general deep learning, we start with a pi candidate, start with pi naught and do some sort of, let's say, gradient descent and get to pi 1, okay, which hopefully improves the objective, and go to pi 2 and pi 3 and so on. That's how we optimize and get maybe the best pi, okay, pi best policy. Here we are saying we are actually somehow we have circumvented in this equation the explicit reference to the policy object itself. Okay, we are saying, hey, forget about the policy objective and optimizing the policy. If we had handle of the optimal state action value, then they're related to other optimal state action values in this way. Okay, so we can ignore policies, okay, and we can directly try to for example, this we'll have one such equation for every state action pair. We'll have many such equations, and then we can try to find q star function which satisfies these many such equations, right, directly. Okay, so we can try to do that, and that's one way. That's one way to get to q stars. Once we get q stars, the policy itself is as following. So if you know a q star, if you have this q star values for every state action pair, then the optimal policy is just a byproduct of it. Okay, the optimal policy is going to be, hey, take the action which maximizes q star of s comma a. Okay, so you're in a state s, so which means that you have q star of s comma, let's say, north, q star of s comma south, q star of s comma east, let's say q star of s comma west. Okay, let's say you have four numbers. Take the argmax. Okay, one of these numbers which is the highest. Okay, let's say q star of s comma west. Okay, and that's the action. So the policy, the optimal policy happens if you had q stars, then the optimal policy is just going to be the action that maximizes the q star at that particular state. Okay, so if you can somehow get to q stars first, then the policy follows naturally, is what I'm trying to say here. Okay, so yeah, so now we're going to transition to the q-learning algorithm, and what I want to do is do again a high level summary of what we've done, because I think the material we're covering covers a lot of things. So we started with a policy, which is a mapping from states to actions, or in general it could be a conditional probability function. Okay, it's a distribution function which says what is the action to be taken for little a given state is equal to little s, yeah, in general, or it could be a deterministic policy like this. Okay, and we also have value function, which is v of s, which is the expectation of the return random variable gt given st is equal to little s. This is little s. Okay, so we had seen this. This is our starting point today, and what we saw with the Markov reward process is that we can add a pi here, right? So we can add a pi here because in the Markov decision process, if we fix the policy, then it becomes a Markov reward process for which this is well defined. Okay, this is just the, if you keep following the policy, you'll keep hitting, next states and next states and next states, right? There's nothing for you to control anymore. And you'll keep, when you hit new states, you'll get rewards. Remember, GT is nothing but RT plus 1 plus gamma times RT plus 2 and so on. So, and this is exactly the expected total reward that you can collect. So this is the state value function. Okay. Now state action value function q pi x comma a, which is a new thing that we defined when we talked about Markov decision process, is nothing but r of s comma a, which is the immediate reward you'll get because you're in state s and you took an action a, plus you can you're going to follow gamma times v. Okay, this probably you might not have seen yet, this equation, but you are in state little s, you take an action a, you'll get to some new state um, s t plus 1. Okay, and from there onwards you follow policy pi. Okay, that's what this is. And in fact, let me take station here. over C is equal to little s. So yeah. So q pi of s is the state action value function, as I said, is just that you have 1 degree of freedom. So now you can pick an action which is maybe the same as what pi is suggesting or something else. And from next step onwards, you take the actions which are suggested by pi. Okay, so that's state action value function. Okay, and that those are the three things that we defined: this, and this. From there, we talked about, hey, these both v pi and q pi, they follow Bellman expectation equations, which is just a recursive. So v pi at a given state is related to v pi at some other states. Similarly, q pi at a state action pair is related to some other q pi at some other state action pairs. Okay, so they follow Bellman expectation equations. Now we also saw, once we have defined the uh, MDP, that there's an objective function. The objective, okay, is to find a policy pi, which is the arg max or pi's that you can get, let's say pi star, the argmax over pi of, let's say v pi of some starting state s. Okay, so you just want to find a pi, which is a policy, such that you maximize the total expected reward. And v pi of s from, let's say, some starting state little s is exactly that, right? It's the expected total reward, right? So you can do this, or you can say this is the arg. Um, okay, let me not write it with respect to q pi. So this is the objective. Okay. If you know everything about the environment, in the sense that if you know the reward function and the transition probability function, you can just, so this problem is just a pure offline problem. Okay. What makes it a reinforcement learning problem is you don't have the model of the environment, okay, beforehand. So you have to interact with the model of the environment, keep, and then try to learn the best by. Okay, and that's what we're gonna go and see next. Okay. In the meantime, we also saw a way to not, while solving the RL problem, we can directly try to say, hey, what is pi star, right? So maybe, after 10 rounds of interacting with the environment, I may have a candidate pi star, and maybe after 20 rounds of interacting with the environment, I may have another candidate pi star. So I may be improving. Okay, so you can keep the policy object and improve it. Okay, that's one strategy potentially. But what we'll use is actually the Bellman optimality equation, which says that q star of s comma a is related to q star at s prime a prime for many such guys. Okay, so that's what Bellman optimality equation says. And here in this equation, there's no, I guess, there's no explicit pi. Okay, so if you could somehow just directly get q stars, then you can get the optimal policy as a byproduct. Okay, so therefore some algorithm strategies can maintain estimates of q stars and then improve them over time, instead of keeping estimates of a policy and improving the policy over time. Okay, and in this, so the idea is, improve estimate estimates of q star function over time by interacting with the environment, okay, or interacting with the simulator, like for example the Atari game that we saw. And this is exactly what q learning, we'll see next, does, and also the DQN algorithm does. Okay. So, in this slide, I've just summarized what we have done so far. Any questions? Okay, if not, I'm gonna, all that language was needed to just, you know, was needed to make you comfortable with how the Q-learning algorithm works, okay, or looks like. The algorithm itself is can be captured in one slide, and it'll look very similar to the simple algorithms that you would have seen, we have seen in bandits, like Thompson sampling, UCB1, and so on, okay. And in fact, you'll see that it's very similar to epsilon greedy. Part of it is actually very similar to epsilon greedy, okay. But um, but there's going to be some changes. So let's look at that. So there's some, yeah. So Okay, let's skip this slide because this is not very critical. So let's look at the algorithm. So as I said, the algorithm is just one slide. So actually, um, and let's talk about a situation where there's only a finite number of states and actions. So there are, let's say, little n states and actions are like 4. Okay, which means that the q star that I need to estimate. Remember, q star is a number. Q star is a function for every state action pair, right? So if I have n if I have a if I want to estimate q stars, if I want to somehow get to q star, okay, somehow, in the sense that that's the optimization problem, that's what we want to learn. Okay, then I just need to maintain n times 4 numbers, right? N times 4 numbers is for every state, for every action, what's the q star value. Okay? So in that sense, you can think of it as a table, right? So here, for example, we are just saying in the first state, for the first action, what is the state action value, the optimal state action value. Okay? That's what we want to maintain, and that's what we want to kind of continue to improve and improve our estimate again and again and again. So we start with some bunch of random numbers, okay, for this table. Let's say we start at state some fixed state S1, okay. Then what we do is it's very similar to the bandit case. You'll have to interact with the environment one step at a time, okay. So t is equal to 1, 2, 3, and so on. And then what we do is very similar to epsilon greedy. We'll take an action which is one of these 4 random actions like north, south, east, west with some probability epsilon. Okay, that's the very similar to the explore idea. And you have to explore very similar to the same reasoning that we saw in bandit. So I'm not going to repeat it here. So with some probability, we'll explore. We pick a random action. Okay. Um, and with some probability, with the remaining probability, okay, we'll take the argmax of the current table that we have. Okay, so remember we had this n times 4 table. Let's say we are in the state, somehow the st happens to be the first one. Okay, so let's say there are numbers, the q numbers, let's say 5, 4, 10, and 3. Okay, then what you do is with this probability you pick the third action. Okay, because the argmax, the number which is the highest is 10 out of these 4 numbers. So the index corresponding to that is a third index, and therefore the third action is you're going to play the third action. Okay, and that's about it. So this is the strategy. The only thing that's missing at this point is how do I, therefore I took an action. So from these two, I picked an action, I play it. Okay, play the action. I'll get some reward. Let's say RT plus 1. Okay. Now, how do I use RT plus 1 to get to a new table? Okay, new table, new Q table. Okay, that's what the rest of the algorithm is going to talk about. Um, so update Q, right? We have taken this action AT, and we got a reward RT plus 1. And we also landed in a new state ST plus 1, because remember, that's what the environment does. It tells you these two things, ST plus 1 and RT plus 1, right? This guy and this guy. Those are two things that the environment has now told me. That's the new information that's revealed. So what I'm going to do is now update some entries in this table that I maintain. Okay, what are those entries? In fact, I'll just update the entry corresponding to the current state and the current action that I took. Okay, there's only one number in that table that I'm going to update. Okay, the update is going to be whatever the previous number plus some some fixed, it's like a learning rate. It's some fixed number. Let's say it's 0.5. Okay, some number times a underlying quantity here. Okay, so the underlying quantity is just using a different location of the same table, that maybe there's some different number, and the current reward that I got, and of course the next day that I got, and computing this term which is underlined, which is called the temporal difference error. Okay, so this error can be, this term can be computed as long as the environment tells me the next state and the reward. Once you know that, you're just adding with a slight correction, with alpha, multiplied with alpha, and just adding it to the current cell number. Okay, that's it. And that's the whole algorithm. Q-learning is just this, and this algorithm has a couple of parameters, epsilon clearly, right, the same as epsilon greedy algorithm for bandits, and also the learning rate parameter alpha. Other than that, there's no other parameters, right? Everything else is you start with the table and keep updating entries of the table. Okay, and you know how to take actions is explicitly what I just we just like mentioned how you take actions. So there's nothing else to do. And it turns out that table, okay, you start with some, let's say, some bunch of random numbers with n cross, let's say 4, you know, and you keep running this q-learning algorithm. Eventually, you'll get a table. Okay, there's 4 actions and so many states, states n cross 4, where each cell, okay, let's say this cell corresponds to little state little s and little action a. Each cell, the number in there is actually equal to q star. Okay, so that's the cool thing about this algorithm. Eventually, okay, if you keep repeating this algorithm again and again and again, so this, let's say, for infinity, for example, then it turns out that the table is actually equal to q star. It's a bunch of those q values, optimal q values that you can get. Okay, there's some assumptions. Remember that there's some these are all random numbers. So this convergence of the table, you know, it turns out the table is, you know, each cell of this table is actually a random variable. So therefore the convergence has to, there's a little bit of more, I guess, technical details which need to be properly said. But let's not worry about that. The key thing is that eventually these numbers look like they are actually q stars. Okay, the optimal q state action pair, state action value function values. Okay, and it's a result from almost 30 years ago. Um, and so it's a quite old algorithm. So the algorithm itself is probably older than this analysis and that folks did. So and that's pretty much it. That's the q-learning algorithm. So any questions about the algorithm, how it's functioning? Um, so the reason why I introduce this algorithm after talking about Bellman expectation equation, Bellman optimality equation, is that this expression here, this update expression, is actually, you know, we can do a series of steps to show that the Bellman optimality equation, uh, you know, is the inspiration for getting to this update step. Okay, so the algorithm magically said, hey, we need to do an update like this. So why is that the case? And the case, you can make that case by looking at the Bellman optimality equation and making a sequence of making a couple of approximations, and you can get to this expression, update expression. But we'll not look at that right now. But other than that, everything else is should be familiar with how the algorithm is laid out. Um, so if there are questions, write it on the chat. Let's take a short break for 10 minutes and resume at 7:50. Yeah. Okay. So welcome back. We're going to continue where we left off. So we're going to so where we stopped is the description of the Q-learning algorithm. What we did not discuss, although we briefly mentioned what a Bellman expectation equation is and a Bellman optimality equation is, there's a way to, you know, at least drive intuition towards why there's an update rule like this. This is the only, I guess, secret sauce or the key step in this algorithm. And the next few slides do talk about it, but in the interest of time, I'm gonna go over. So this is going to be our starting point, and what we'll do in this next few minutes, next half an hour or so, is we're gonna bring back some deep learning into the picture. Okay, and that's where that will give rise to a slightly different algorithm, which is called DQN algorithm. First thing to note is that in this update rule, in this whole for loop, okay, what we're doing is at every time step, we are interacting with the environment, right? So we pick an action. So this is what we do. First 2 bullet points is what we do. And of course, the third bullet point is what we do. But between the first 2 and the third, um, there is an environment which gives us back, right? So it gives us back. We play AT to the environment, and the environment gives us back ST plus 1 and RT plus 1. Okay, so those are the 2 objects that the environment is giving back, and we are sending AT. Okay, so there's an update happening every time we interact with the environment. Okay, so if you think of environment as a function, we call that function given action A, it produces the next state and the reward. and those two are the two new things that you get, and based on that you're updating your Q table. Okay, so with DQN you'll see that it's slightly different of how we update the Q table. In fact, we'll drop the notion of a Q table, but the rest of the idea is going to be very similar. Okay, the rest of the idea is just explore exploit. We saw all this in Excel and greedy, so the same idea here. It's just that the way we'll try to get better and better Q star. Remember, Q star is what we're trying to get to, and pi star, which is the optimal policy, is just a byproduct of getting to Q star, right? So that is the same idea. So how do we get to Q star using in a slightly different ways, is what we'll see with DQN, and you'll also see why DQN is needed. Why not stop with this algorithm? Okay. So with that, let me switch over to a different set of slides. Okay. Okay. So this is the next set of slides, module number 12, I think. So I think the chat function is hidden. So let me see. Okay. So what we'll do is, so there's actually, we are pretty close to defining the DQN algorithm or the DQN modeling approach to solve the reinforcement learning problem. But there's one, we're pretty close except for one thing, which is about function approximation. Okay. And we'll first motivate function approximation or value function approximation, and then get to defining the DQN technique. And this is where we want to stop today, ideally. So let's get started. So I'll skip so this first few slides are again revisiting the idea of how do you go from Bellman optimality equation to that update rule that we saw for the Q learning algorithm. Okay. So we will not do that. I mean, you can see that this is the update rule for Bellman optimality equation. There are some approximations that you can do step by step of this and that. So we'll skip that. We can take up this maybe after the session or offline. Okay. But let's come back to this was the state of affairs right before the break. We saw this algorithm, which is just this much. Okay, every time step take an action based on epsilon greedy approach, and then update an entry in the Q table. Okay, the problem is keeping a Q table is not enough, right? And in fact, most of the examples that I showed you at the beginning of the session involved complex states, right? The states are not just numbers. It's not the numbers on a maze of the toy example that we saw this time as well as last time, where the state was just, hey, one of the boxes, which is XY coordinate, cell number 2, 3. Okay, that was the case in the maze example, where you had to go north, west, east, south. Whereas in the demos that I showed at the beginning of the session, the states are not that. The states are actually, in fact, turns out the state is actually given by the video feed. Okay, even for let's say the self-driving car, which can not just have video feed, camera-based feeds, but also other measurements using other technologies. Or in the game playing setting, like for the Atari game itself, the breakout game, we have a screen, okay, a frame, right, that's being shown. Or in the Doom game, or the Flappy Bird game. For all these cases, actually the state is not a finite quantity. I mean, so the number of states is not finite, right? It's not just 10 screens. There could be many millions of screens depending on where you are, where the new, I guess, enemies and so on are, and so on, right? So, and here is an example. So if an agent is navigating in a real world, on the left side is a top view where the agent's position is just a position in a grid. Okay. In that case, maybe the number of states are finite if you grid everything. Okay. And your actions are those 4 north, west, east, south, or forward, backward, left, right. But this is rare, right? So why would a real world environment be, represented in this way? Most often, it's not going to be like that. In fact, you'll have a camera view or some other view or some other type of measurements, okay, and they'll not be finite in number. The number of stations aren't going to be finite. So in that case, you need to do something more, and that something more is what changes Q learning to DQN, for example. And that's the idea of function approximation. So it's basically the idea that instead of representing a Q star, I mean, anyway, we started with Q star as a function going from state from A any state comma action pair to some real number, okay, like 10 or something. This is equal to 10, let's say. So anyway, we had this, but in Q learning, this is equal to 10. In Q learning, we said, okay, instead of that, let's keep a table, and then hopefully this, is closer and closer to Q star, which is every entry is a Q star, a little Q star for a state action pair, right? So estimate, I guess, estimate Q star was the idea behind Q learning, right? So instead of that, let's come back to just maintaining some estimate. I mean, I don't want to give, let's call it Q bar or QT. Hopefully it'll converge to Q star after a long enough time, after enough interactions with the environment. Okay, we'll come back to functions rather than tables. Okay? And any functions can represent many things. Functions can represent the value function. I mean, functions can represent also policy, because policy is also a function, and functions can also represent model, because a model, a probability density function, is also a function, right? By definition. So uh, if you can represent, in particular, if you can represent these functions using deep neural networks, or in general neural networks, uh, either the value function, the policy function, the model. In particular, since we're talking about Q learning, the only function that we care about is actually the value function, or the optimal value function. If you can represent that using a deep neural network, then we get these updates, right? We play an action, we get some next state reward, and so on. We get this data. From the data, we can somehow update the parameters of this neural network, neural network, which represents our value function, state action value function. Okay, that's the key idea. Okay. And we can do this update as long as this function is differentiable. And many deep learning neural network architectures, they are all differentiable, right? And we can just use gradient descent methods. So that's the key idea. So in terms of pictures, what is happening, right? So instead of storing a table, which is number of states as rows, and columns corresponding to actions, we represent it using a function. Okay, so for a function, we're going to introduce an extra, I guess, argument in the way we define it. So the argument is going to be the extra argument is going to be the parameters of this function. Okay, so what we're going to do, and that's where the approximation comes in. The true Q function could be something. Okay, so the true Q star function could be whatever. We don't know it, right? If we knew it and there's no learning to be done, we just have to take a policy action based on that. We don't know Q star, this quantity here. What we want to approximate it by is using an approximating function. Okay, and that approximating function will have parameters. Okay, and generally, and let's call the parameters little w. Okay. So what we can do is, if we had that, if we have this approximating function, then what we'll try to do is adjust this parameter such that this function on the left side is as close to the function on the right side. Right? That's what a good approximating function is, the one which approximates the original function, right? So either you can say, hey, state and action is the input, and I get to choose w, keep changing it, I get to choose w such that I can get q of s comma a with this parameters w. Or an equivalent way to think about it, and it's going to be useful for us, is I just pass the action, I just pass the state. Okay, and for every action I produce a number. Okay, that's like saying, hey, let me remember in the Q table, every state, and there was like rows for every action, a1, a2, a3, and a4. Okay, I'll just give you the state as the input. Give me all the 4 numbers at one time. You can do that. A function can do that. It's not exactly it's basically the state action value function evaluated at multiple actions, at all actions. Okay, so we can do that, right? So, but even then, if you want to do this second type of given some input, produce some outputs, again the same type of parameters apply, right? If you change w such that the first output is as close to the q star of s comma a, the second output is as close to q star of s comma a2, and so on, right? So that's just a, I guess, a diagrammatic illustration of what we want to do, okay? A function approximation of the true q star, which we don't have a priori. So that's the problem of reinforcement learning. And these functions, by the way, this function represented by this box can be linear functions, decision trees. These are things that you've seen before. Neural networks is what we've been studying in this course. Other functions, nearest neighbor, you can use any function to approximate, to given an input, produce an output, right? can do that. Now, what is so for the next couple of slides, I wanna uh, I wanna motivate how you change these parameters. How would you learn these parameters? We've already seen gradient descent as a way to update parameters, but I want to define a suitable optimization problem here. Of let's say you already knew, let's say for a given policy, you already knew q pi of s comma a. So which means let's say you already knew this thing which I'm underlying or overlining, right? Let's say if we know that, how do we get w? How do we get a good w? Okay, let's say we choose a linear function class, for example. How do we get good w? So the way to get good w is to define what is meant by good w. So we have to define a notion of goodness, right? So that's through a loss function, right? So we can say, hey, you've given me q pi of s comma a. That's a function that's given to me. I want to find an approximating function from an approximating function class, like a linear function class, which means that I need to find w's. Okay, I can say, hey, what w's can I choose such that these two, the difference between them is as close to each other as possible, given as a function of given policy. Okay, the policy is just so that we don't, it's just for simplicity for this example. We'll look at the true objective. We'll come back to Q learning in a second. So let's say we define a function. Now this objective, this is the objective for every w. For every w parameter, it will tell me whether the approximating function is good or not, right? If I knew this, okay. In general, we don't know this. In fact, in the RL problem, we don't know this. Okay, the one I'm signifying by the arrow. Now, if the objective function is like this, and we want to change w, we already know stochastic gradient descent. In general, we know gradient descent. We just take the gradient of the loss function of the objective with respect to w, and in this case, since it's a squared loss, we can get something like this. It's just the some y minus f of x whole square. If we find the parameters, of this thing, okay, you'll see that the gradient is like this. Okay, it's just the it's just the gradient f prime, or not f prime, but let's say, let me write it, gradient of w with respect to f of x with w times y minus f of x. And there's also two factor, okay, minus two factor. So that's what this is. Okay, and that's why you multiply with minus 1/2 to get rid of minus 2, and then this is the expression. Okay, if you take the gradient, and if once you have the gradient, you can always update w. So delta w is just w new minus w old. Okay, w new minus w old is exactly equal to the gradient, right? So negative gradient, right? So some learning rate times the negative gradient. Okay? So sorry, if you want to do gradient descent, so yeah, yeah, we want to do gradient descent, and so this is just the update equation. So this should be familiar for most of you. We've seen this gradient descent idea probably in the first or second session. So this is how you do if you've already been given a target function. Okay, but in general, we have not been given a target function q learning. Okay, but let me complete this example by saying, hey, what if this q hat is actually a linear function? How does this update look like? Just to finish the narrative here. So if we want to have a linear function, then let's say from state to actions, we have a vector. Okay, so these are like features. So given state and action, let me compute a feature vector. Okay, let's say that's given. Okay, there's no parameters here. It's just literally, for example, you can say state action is just s, s and a. Okay, like if state is represented by a vector and action is also represented by one hot encoded vector, you just concatenate them together. That, for example, is a feature vector. Okay, given that feature vector, you can say, hey, q hat should be equal to a linear function, right? So that's w transpose the feature vector, or w transpose feature vector, right? So if my approximating function is like this, then how would your gradient update look like? Gradient update would be the gradient of the function itself is just the feature vector itself, right? So because d by dw of x transpose w is just x, or x transpose, whichever we want to call it. So it's this. So therefore, the gradient update, and this should be familiar if you're just solving. If you have a squared loss and if you have a linear function, then this is the gradient update. Okay? Just to complete the story. Um, So, but as I was saying, I've been repeatedly saying, we don't know q pi of s and a. In fact, even if we, even for a given policy, we don't know q pi of s comma a unless we interact with the environment again and again and again and get a good estimate of q pi of s comma a, right? So, but so instead of trying to directly say, hey, what is q pi of s comma a, let's come back to our q learning update rule. Okay, so our q learning update rule was this. In the table, remember the table update rule, it said, okay, if you take an action AT and you got response RT plus 1 and ST plus 1 back from the environment, okay, so you went to a new state, a new screen, and you saw an instantaneous score increase, decrease, let's say if it's a game, then you got those two back. Then the update is like this, right? Q of S is just the previous value plus some learning rate times something called the temporal difference error. Okay. Now, this is a Q learning update, but if you remember at we also know that if we do these updates, we know that Q learning gets to Q star, right? Eventually, and Q star is the optimal Q state action value function. Now, at Q star, you can imagine if this is Q star, let's say we get to Q star. If this is Q star and this is Q star, then this should necessarily be equal to 0, right? This term should be equal to 0. Right. Eventually, if we get a Q star, if we do a Q line update, if this is also Q star, if this is also Q star, then this should be 0. Or in other words, what I'm trying to say is that at optimality, basically you don't want this temporal difference error. Okay, it's called temporal difference error, just nomenclature, and there's reasoning behind it, but we have skipped that. But what I'm trying to say is that at optimality, you basically want this. There shouldn't be no correction term. You need to hit the steady state, right? So there should not be any more updates. If you have hit Q star, if you're already at Q star, there should not be any update, which means that this extra thing should evaluate to 0 in expectation. Okay, in expectation means because these are random variables, so you need to take expectation. So in expectation, that term should be 0. The error term should be 0. Okay, so this motivates us. Remember, our problem was we did not have the for example, the q pi of s comma a, or in general, we also don't know q star of s comma a. If we knew it, then there's no learning problem at all, right? Since we don't have these guys, in particular for q learning, we don't have this guy. What we can do is, but we know that we need to have temporal error, temporal difference error, sorry, should be 0. We can convert this into some sort of a squared loss function. If this has to be 0, then we can say minimize. So if this has to be 0, and we're going to do a function approximation for these two, instead of tables, if instead of keeping tables, if we have functions, in fact, function approximators, which is this, with an extra coordinate, right? Extra argument, which is the function's parameters. Then we can intuitively minimize these two terms, the difference between these two terms and the last term. Okay, and we can just use a square loss type of an error, square loss type of an objective. And that's exactly the change that we're going to do from the original Q learning algorithm. So now we're one step closer to the DQN procedure, where we're now going to focus on trying to minimize some sort of, we're trying to update W when we get feedback, when we get the next stage reward type of information. We're going to change W so that we can get this, first term closer to first two terms closer to the third term. Okay, so that's the key idea. But before we come back to the step, let me talk about this DQN algorithm, what its history is. It's from 2013 or 2012. So here's a screenshot of many of the Atari games. I think this one is breakout here, if you can see. But so for all these games, the same algorithmic approach worked pretty well. Okay, and before I come back to what exactly is the DQN's approach of like what is exactly minimizing and where is the neural network explicitly, let me talk about what is the issues with function approximation that you should be worried about. Like you can't just arbitrarily change from table to a function and the original algorithm may not work. Okay, the update algorithm that was there in Q learning will not generally work. So there are some issues. Okay, let's talk about them. generally there's going to be a non-linear, non-linear optimization over W. Okay, so if you bring in a function approximating function, then you'll have to optimize over W instead of updating table entries, right? But that optimization, even if I just motivated saying that, hey, maybe there's some squared loss type of thing that we can do between these two terms, that objective function may not be a nice objective function. But that's not too much of an issue because we have had crazy objective functions or crazy loss functions for when we were doing deep learning with so in the supervised learning setting, right? So that itself is not an issue. Um, but the issue is we may not be able to do this in Q learning. We were doing an update of a table entry every time we interact with the environment. Okay, instead of that, maybe we should do something by doing batching of the experiences that we get from the the feedback that we get from the environment. Okay, this is very similar to what we do in supervised deep learning, right? And next thing, which is quite important, which is very different from supervised learning, and that's where I think even last session somebody asked what's the difference between supervised learning and reinforcement learning, is this idea that the data is not IID. Okay, because your current action depends on history. Okay, and it also influences rewards that you can get now and in the future. The data is not, if you think of data as, let's say, state, um, think of data as state, action, next state, and let's say reward. I drop the indices of time. So if you think of this four tuple as one observation, and at the next time it's like S prime, some A prime, and S double prime, and then some R prime, some tuples like this, these are not independent. Okay, and that causes a lot of issues with optimization. And um, there are other things. For example, there's a, if you look at this, there's a max operation here. If you think of a if you think of a defining an objective function with a max operation inside, there is, it's not a nice function. Okay, it's not a, it introduces sudden changes, right? If your max suddenly changes from 1 to 2, like action A, action 1 was maximizing the q value currently, but now suddenly action 2 maximizes the q value. That's not a nice thing. So that leads to sensitivity issues. Okay, but anyways, summary is that naively optimizing or W doesn't make sense, and you'll see that in addition to changing from incremental update, remember the original Q learning was incrementally updating things. In addition to changing the objective and now updating W's, we'll also do some extra tricks. Okay, and that's what the extra tricks are related to. I'm going to describe them, and those precisely try to address this issue of naive optimization. We'll certainly do something related to batching, very similar to supervised learning or very similar to supervised deep learning that we were doing before. But in addition to that, we'll do a one or two more steps. Okay, that's what this is trying to motivate. But I'll tell the steps in a second. Any questions about the function approximation idea of how we are moving away from tabular idea of the Q learning algorithm to the DQN algorithm, which involves function approximation? That's first thing, core thing. And in addition to that, because data is not IID, it will also take care of it'll introduce a couple of engineering tricks roughly, and that completes the definition of the algorithm. Okay. And this new algorithm deals with uh, state spaces not being finite, not being 10 or 20, but for example, screenshots like the Atari game. And so that's a big step up from what was there before. Okay. But this is just one algorithm. We're only getting, so we saw Q learning, that's already one algorithm for solving reinforcement learning, but it only works for small toy problems. We're going to look at the next one, which is DQN, which at least makes the state space not fixed, not finite. Sorry. Okay. Um, any questions at this point? Okay, let's now talk about the algorithm. So we'll look at DQN that was originally designed for Atari games, and has been used for many different approaches since in the past decade. So um, yeah, so DQN is an example of a deep reinforcement learning algorithm, and deep reinforcement learning algorithm is, as the name suggests, introduces neural networks, or nicely uses the deep learning functions, or neural network functions as function approximators. Okay, for either value function or policy function and so on. We are anyway concerned with approximating the value function, state action value function. Okay, so we look at DQN from 2013. And why deep representations? I will really not talk about this. We have already discussed this, that deep networks with con layers have really improved performance over in the early part of the last decade, and so they're much better in approximating, much better with dealing with, for example, image type of state space, or image type of states, for example. Um, and CNNs are used as function approximators, in addition to anything else. Okay, in addition to fully connected layers, sorry, fully connected networks or other networks. Okay, but I'll not discuss why CNN can be function approximator and so on. But it suffices to say that in DQN, or sorry, in Atari games, we actually have images, screenshots of games. Okay, and there it's very clear that maybe since we have screenshots, they're actually images. So you can imagine the function approximator can be a CNN, okay, or CNN-like architecture, right? So let's come to the DQN details. So what's happening, right? So we have the screenshot. Okay, that's the observation. And here's, I mean, this is the algorithm that we are going to describe next. But it gets the observation and takes an action. Okay, the action is actually a joystick action. So the joystick, simulates like a finite number of actions, like whatever, 10 or 20. Okay, and that's fed into the console, right? So the console now simulates, right? Simulates that, hey, something moved, some action happened, and based on that, at the top of the screen, there's a reward. Okay, and the reward is fed back to the algorithm. Okay, instantaneous reward change is fed back to the algorithm. Okay? So um, and this is the simulator. Actually, it's actually a physical simulator, but you can also do this with the other simulators that we saw early in the session. Um, Yeah. So that's the setup. So and DQN uses Q learning. Starts with Q learning, uses CNN as an approximator, and it does, as I said, two things. Okay, two things to fix the IID issue, the data dependence issue. Okay, which makes the optimization. The moment it uses CNN as an approximator, you can imagine there's going to be an appropriate loss function similar to when you're trying to optimize CNN. You would in a classifier, you would minimize cross entropy loss, right? Similarly, here there's going to be a slightly different loss function you're going to optimize for. Okay, because it has to be motivated from the Q learning update and all that. That's one thing. But in addition to that, there's going to be two more, I guess, changes. Okay, to deal with this data being not like how you'd have data in the supervised learning case. Okay, first thing is um, yeah, first thing is batch optimization. Okay, which is something that we would do even supervised learning, but this batch optimization is also addresses this issue of data not being IID. Okay, so batch optimization, but it addresses the IID issue, and I'm going to talk about that. And there's a specific name. I will get to that in a second. Second thing is freezing the targets. Okay, so I'll talk about what is freezing the targets, what is target, and what does it mean by freezing in a second. So, okay, these are two extensions in addition to using a function approximator. Okay, that defines the key essential characteristics of the DQN approach. So let's look at the function approximator for a second. It's basically the input is not just one screen. It's actually the screen and the previous three screens. So four screens. They are 84 cross 84 in dimensions, in height and width, and they're four screens. Okay, and then we have the usual, 8 cross 8 filters, 4 cross 4 filters, and then a couple of a couple of fully connected layers. So, okay, so it's a it's really not a deep network. Okay, it's a really shallow. It's only 4 layers deep, right? 4-layer deep network, and the action space is just 18. Okay, so the 18 actions. So it's like 18 class classifier. It's not really classifier. The object function is different, as I said. but just has a output which is 18, which produces 18 units, okay, 18 numbers. And reward is, as I said, is a change in score for that taking that action. And the change in score is shown at the top of the screen typically, and that's the function. Okay, now um, let's talk about what the objective function and looks like, and also these two fixes: the batching idea and the fixing the freezing the targets idea. Okay, so the batching idea is called experience replay, and the fixing the targets or freezing targets idea is called fixed queue targets. Okay, so let's look at that. So how does the algorithm work? Okay, you take an action according to the epsilon greedy policy. That's exactly what the original queue learning algorithm is doing. Next, you store this transition. So store this tuple. Okay, what state, what action, what is the next reward, what's the next state. Okay, store that in a in an array or in some storage location. And in fact, it's called a replay memory called script D. Okay, so you store that. Now what you do is actually sample a mini batch of such transitions. Okay, from D. Now if I sample from D, so although in D I was storing bunch of such 4 tuples, right? When I sample, I'm gonna get the first guy, I'm gonna get the third guy, I'm gonna get the 10th guy, and so on. So already, the correlatedness or the dependence between the samples is already eliminated when I sample, at random, right? From D. I'll sample a mini batch, maybe 10 example, maybe 10 such tuples. Okay. Once I do that, then I'm gonna do then I'm gonna compute Q learning targets. Okay, and what are targets? I'll show you. These are based on fixed parameters, and these are the not. So these are based on fixed parameters which we are not training. Okay, which we are not learning. Okay, and then we're going to try to minimize the difference between our function approximator, the Q network, and these targets. So what are the targets? To be more specific, these are the targets. Okay, the targets are nothing but these weights are frozen. Some old fixed parameters, some old previous weights. Okay, and given those all previous weights, given this mini batch, I'll get the S prime A prime from the mini batch, and I'll compute these targets. Okay, these are like Y. Okay, so Y, right? The targets are dependent variable. Okay, dependent values. So I'm going to do Y. I'm going to get the Y, and then state action for every state action pair in my mini batch or in my batch of examples. I'm going to compute that current function at the current weights minus Y the whole square. Okay, so this is my loss function. Okay, this is a loss function at the current W iteration. Okay, current W value, current weights of my neural network. Okay, so I can just use stochastic gradient descent to update Wi. So I'm going to go from Wi to Wi plus 1. Okay, so that's the key idea. Now, and in this slide itself, you can see the 2 steps, right? So this mini batch is the idea which is related to experience replay. Okay, and fixed Q targets is precisely this idea. Okay, so your targets are fixed in the sense that they're, this Wi minus is not an optimization variable. The only thing that you're optimizing is Wi. Okay? And how did this loss function come about? Is exactly the loss function that we saw several slides ago, where I was motivating that, hey, here's the error term in the Q learning update rule. The error term, we can intuit that, hey, if the error term has to be 0, some squared error of squared difference between the error term, the square difference between the first, second, and the third terms has to be 0, and that's how you get to this objective. Okay, so, and here's the picture of that, and we'll probably stop here. Okay, so what's going on? So as I said, you have this function. Okay, this is the function approximator. Okay, this is a function which is a Q function. At any given point of time, if we have a Q function, as I said, we can always come up with a policy, right? The policy is just going to be, hey, if you're in state S, find all the actions, okay, that you can take, and whichever action has the highest Q value, play that action with 1 minus epsilon probability, or with epsilon probability, play a random action. So we know how to take argmax or take an arbitrary action. We know that, okay, and we give that to the environment. The environment responds back by giving me the next state and the reward. Okay, that information along with my current state and reward, current state and action, I'm going to store it in a memory. Okay. And once I store it in memory, now how to update it? I'm going to pick a mini batch. So SA, S prime, R prime is one example in the mini batch. With S prime and R, with S prime and R, I'm going to define the target. Okay, so this is a target. So with S prime, A prime, and R, I'm gonna define the target. Okay, so A prime is not given. A prime is just the action that maximizes given the S prime. Okay, I'm going to define the target. And then with s comma a, I'm going to define my function value. Okay, and the function parameters here I'm showing as theta. Think of it as w. I'm going to go from wi to wi plus wi plus 1 using gradient descent. Okay, so gradient descent. And that's it. That's a deep learning algorithm. Sorry, that's a deep Q network or DQN algorithm. Sorry. So with that, let's pause because there's the next slides are just talking about, hey, it performs really well. I would suggest looking at this paper. Uh, yeah, I don't have a link to the paper here. Yeah. Um, yeah, I can give a link to the paper. It's actually there on the syllabus page in the notes section. So have a look at the underlying paper, the DQN paper. It's, uh, it's linked on the syllabus page. So with that, let me pause here and see if there are questions about the algorithm. I mean, this is in your assignment, so it's good if you have some questions. If you have questions, certainly ask me after we end the class. You can also ask me now. So in the assignment, this environment is going to be the cart pole. You have a pole and you want to push the cart left or right so as to balance the pole to be vertical as much as possible. Okay, and the instantaneous reward is what's the position of the pole versus what's the ideal position. Ideal position should be vertical, and pole could be left or right, or it could have completely fallen down. Okay, that's the difference between those two situations is the instantaneous reward you can get. Okay, and and the Q function, exactly works the same way. In cart pole setting, you don't have to. Your state doesn't have to be the picture of the cart pole, right? So it's not an image like Atari setting. There you can have just instead of a CNN based function approximator, you can have a simple fully connected layer, simple feed forward network. Okay, so that's the only change. Otherwise, everything else kind of remains the same. There has to be experience replay. There has to be also target freezing. Okay, and when you're minimizing the loss function. Once you freeze the target, you can think of this targets as just some new dependent variables, right? Dependent variables that you're trying to optimize your current queue function towards. Okay. So with that, let me end the session. Please, if you have questions, stay back and ask. And otherwise, have a good rest of the evening.